All right, so to wrap up the year here, what you can see, we're going to be working on exponential functions. Now, this last unit is going to be on not just exponents, but logarithms. And one of the things that you're going to want to understand is that exponents and logs are really one and the same. Now, I'll get to the point where we talk about logs after we really introduce our exponents. But again, exponents and logs almost always go together in one way, shape, or form. But let's start talking about exponents and what they are. So I have some data here, and what I'm going to do here is just talk about the relationships. So this first set of data is actually going to represent something that we hopefully are very familiar with, and that's a linear function. And the reason why we can tell if a set of data is linear is based off the output, and it has to be a consistent number, but the key on that consistent number is that it's a consistent or common difference, which means you are adding or subtracting a common number every time. So for this first example, you're going to see that this 5 becomes an 8 because you're adding 3. And then you add 3 again, add 3 again, and you add 3 again. So if I was going to write this equation, what we would do with it is we'd put it in this form called slope-intercept form, where b, that number right there, is your initial value. So we'll call it the initial. It's also called a y-intercept. For sakes of what we're going to do right now, I'm going to call that an initial value. Now this next number, this is going to be that rate. And in this case, the rate is whatever number you're adding or subtracting each time. In this case, we're adding a 3 each time. So our equation would look like this: y equals 3x plus 5. And again, we should already know how to do that, but that's just, again, a quick example of how we find linear functions. Same thing down here on this next example. We are here subtracting 2 every time. So this equation would be y equals negative 2x, because that's my rate, plus b, which in this case is plus 12. And that's how we do, again, linear functions. So what's an exponential? Well, it's kind of related to the linear in a sense. It just has one key difference. So in this case, we're looking at a set of data, and here, if you kind of look at it at first, you say, well, it looks like I'm adding 4, but then when you kind of look at the next set of numbers and the next set of numbers, you can tell that's not the case. So another thing that could be happening, which is what's happening here, is I'm going times 3. So we are multiplying, and if you notice, if I keep doing that, not plus 3, sorry, if I go times 3, you're going to see that 6 times 3 is 18, 18 times 3 is 54, and so on. So in this case, what we do is we put it into a form that we use for exponential functions. And this, if you have your notes printed out, this is the exponential function form. It's got the box. So for exponential functions, we are going to have the following form. It's going to be y equals a times b to the x. So this is the standard form of an exponential function. Now the standard form of a linear function is y equals mx plus b. So we're going to take some of these same concepts and apply them over here. So the way what we're going to have to do here when we have a exponential function, this value right here, that's my initial value. It's kind of like your y-intercept, where b is your rate. Now the thing that changes is your rate is not a number that you're adding or subtracting every time. It's the number you're multiplying by every time. So in this case, that rate is going to be 3. Notice your initial value is still your y-intercept, so it will be 2. So we're going to have y equals 2 times 3 to the x. And this is your exponential function. Now, the way it works here, and you can kind of test it if you wanted to do a couple of times, like if I was going to take this number and I wanted to plug in, say, 0 for x. So you'd have y equals 2 times 3 to the 0, which 3 to the 0 is 1, so we get y equals 2. So you can kind of see how that matches up. If I want to plug in another number, let's say I just want to plug in 2. So you're going to plug in 2 times 3 squared. Now what's happening is you're taking this 3, and you notice from the first point to the second point, you're multiplying by 3 twice. and 3 squared is multiplying by 3 twice. So this would be 9 times 2, which is 18. So we end up with y equals 18. And again, you can kind of see that pattern. So again, we have our standard form for an exponential function right here. So if I wanted to do this next example, you'll see as I kind of go down the line here, we are going to be, in this case, dividing by 2. But a rate is not a common divisor, it's a common multiple. So if I was going to do a common multiple here, you want to look and say, well, the same thing as dividing by 2 is multiplying by 1/2. So here, if I just kept multiplying by 1/2, I would have a constant rate, and you'll see that it does match. So here, this equation is going to be y equals a times b to the x. A is going to be your initial value, so 32, times your rate, which in this case is 1/2, to the x. So we have two types of functions here. We have this first type, and it has a name. If the rate, so I'll put it right up here. So if b is greater than 1, which it was here, b was my rate, it was 3. Notice your data is growing. So this is going to be called an exponential growth curve. And then here we have b, which is my rate, was less than 1. It was a fraction. So here, if b is between 0, sorry, I ran out of room there, but if b is greater than 0 and less than 1, so it's a fraction basically between 0 and 1, this is going to be an exponential decay curve. So basically the next thing to see is what does that look like? So we'll kind of go on to that next. Okay, so what we're going to do is we're going to consider an exponential growth example. We're going to consider this our example that we're going to be graphing for exponential growth. So you'll notice the rate is greater than 1, whereas our decay example, the rate is going to be between 0 and 1. So to kind of show the difference on these, this is both of these are very basic forms of your exponential functions. They're related to your parent graphs, which we've already studied. So some of the things that we should already be aware of. If I take this function, I kind of break it up a little bit in terms of a and b. This is y equals 1, because there's no number there being multiplied, so we call it a 1, times 2 to the x. So this 1 is our y-intercept. So if I come up here, I go to 1, and I have a point at 0, 1. Now, from here, some of the things that we already know about our exponential functions from our parent graphs is that they're going to approach a horizontal asymptote at y equals 0. So I'm going to put a horizontal asymptote at y equals 0. Now again, the question would be why? Why do they approach y equals 0? Well, one of the things that you'll realize here, and I'm just going to do a little example off to the side to show this concept, when you graph this function, actually let me graph it first and I'll show you, but as you graph it to the right, as we already know, is that your numbers are going to start to explode. I mean, it's not that big at first, but it doesn't take long for it to really take off. Now, without plotting a bunch of points for this specific example, I'm really wanting you to see the curve, and it curves up. And I'm only going to graph to the right or the positive x values, and you're going to get a curve that starts to take off pretty quick. Now, it's not a line, it is a curve. Now, what happens when you go to the left? Well, when you go to the left and you start plugging in numbers here, I'm going to pick a couple examples. So let's say I plugged in, and I want to do tiny, this is a very tiny little xy chart. That's an x right there, it's super small, xy. So if I plugged in, say, -1, I'm going to go -2 and -3. I'm just going to plug those off to the side so you see what's happening. So if I plug in -1, this becomes 2 to the -1. Now, knowing your exponent rules, a negative exponent is going to get moved to the bottom. It's going to become a positive exponent. So this becomes 1/2. Now, if I plug in -2, we get 2 to the -2. Well, that becomes 1 over 2 squared, which is 1/4. And next, if we go 2 to the -3, that becomes 1 over 2 cubed, which is 1/8. Now, what you'll notice is this graph, or the function, all these numbers get smaller as I go to the left. So what's going to happen with this scenario is that my numbers are going to approach 0, but because that 1 is always going to be on top, it'll never actually touch 0. So as I go to the left, it's going to start to flatten off. It's going to be approaching 0, which is your horizontal asymptote. So we're going to graph it like that. So that's going to be exponential growth curve. It's always going to have that look to it. Now again, your y-intercept can change, your rate can go up faster or slower, but it always has that look. And then next up, your exponential decay. Now all this really does, instead of it going up, it goes down. So you can kind of see your data here. And if I follow this example that I already did earlier, what you'll notice is if I keep cutting this in half, what ends up happening, if I kept going, this would be half of 2, which is 1. Then I'd have half of 1, which is 1/2, half of 1/2, which is 1/4. And it's just going to keep going smaller and smaller. And you notice it's going to approach 0 again, but it won't touch it because of that 1. So if I come back over here, you're going to have your horizontal asymptote. It's just going to approach it from the opposite direction. So I'm still going to go through 0, 1. And again, you can label that point if you want. I didn't do it up here, but I can. It still goes to that same point. It just flips it over the y-axis, really, if you think about it. So it's going to start up here. It's going to come down pretty quick. And then it's going to kind of level off as you go to the right. So again, that's going to be your exponential decay graph. So your growth graph and your decay graphs, all they are reflections of each other. All right, guys, so now we're going to graph a couple of these, and we're going to kind of see how some of these things work in terms of some of in terms of really, I'm trying to label all this important information we've been talking about, including some things we've talked about in the past, including domain and range. So to get started here, we have our first example. Again, all I want you to do is graph it, and we're going to identify all the key characteristics that I have labeled here. So the first thing we want to be able to do is take a look at this equation, and we're going to look at this rate. Now that rate is a number between 0 and 1. So what that means is we are going to have a decay graph. So we should already know the general shape of this curve. I'll get the domain and range at the end, but what I can do right now is get my y-intercept, because this thing is technically being multiplied by a 1. It's a really tiny 1 I'm putting right there. So that means my y-intercept is at 1, so 0, 1. So when I come over to my graph, I'm going to go right here at 0, 1. And the asymptote, we know, is going to be at y equals 0. So this graph's going to approach 0. So I'm going to have an asymptote right here. And again, it is a decaying curve. So when I graph this, I know it's going to be going down. So I'm going to have this shape right here. And again, it's going to flatten off as I go to the right. So that's my graph. Now that I have my graph, I can do my domain and range. Now for the domain, it still goes left and right forever. So we're going to say the domain is all real numbers. Next, our range, it does start at 0. It doesn't touch 0 though, because it's never going to touch it. So we're going to have a parentheses here when we do our set notation. It's going to be 0, infinity. So it's going to go off to the right forever. And lastly, our end behavior. So for our end behavior, we have the limit of, in this case, I'll call this f of x. So the limit of f of x as x approaches negative infinity. Well, as I go to the left, I'm going to negative infinity. Notice this graph is going up, so it's going to go to positive infinity. So that's your end behavior as you go to the left. And next, the limit of f of x as x approaches positive infinity. As I go to positive infinity, I'm going to the right. Well, this graph is approaching that horizontal asymptote at that point, so it's going to approach 0. So that's all your important information for an exponential decay example. Moving on, I'm going to go over here to our next example. Now this one, you'll notice, has an a value. So we have, this is my a, and remember this right here is my b. So again, a couple things. B is 3. It is a number that is greater than 1. So this is going to be a growth curve. Now be aware, if I had something like this, like 1/2 times 3 to the x, then that's something that can easily throw you off if you don't pay attention to what's what. Again, 1/2 wouldn't affect my rate. So if that's 1/2, don't be like, oh, there's a fraction in here. It must be a decay curve. Remember, it's the rate. That's all that matters. Now I don't have a fraction here, so it doesn't really matter. In this case, it should be easy to tell that it's growth, but be aware of that. Again, it's the rate that tells you it's a growth. It doesn't matter what the y-intercept is. It's the rate that does that. So anyway, we have the growth curve. Our y-intercept in this case is a, so I'm going to come down here. A in this case is 2. So my graph is going to start up here at 2 now. So 0, 2. And think of that that number, just like we do with our other graphs, if you multiply a function by a number and that number is greater than 1, it's a vertical stretch. So we still have a vertical stretch. So you'll see your graph's kind of being stretched. It's going to be going up a little bit faster here than it normally would with that rate. So that's what that y-intercept is doing. It's stretching your graph. I didn't mean to do that. It's stretching your graph a little bit vertically. Your asymptote, though, I haven't done any, and we aren't doing those at this point, any vertical shifts. Now, that's the only way you're going to get your horizontal asymptote to change. I'm not doing that, so it's going to be y equals 0. So I'll go ahead and put that right in here. And your end behavior, well, let's draw your graph before we do that. So your graph is a growth curve, so it's going to start down at the bottom over here by 0, and it's going to come up through 0, 2, not 0, 1, and it's going to take off forever. So your domain, your range. Your domain, again, is all real numbers. You're going left and right forever. Your range is going to be 0 to infinity because you're starting at 0, which is your horizontal asymptote. We don't touch it, so I put the parentheses, and it goes up forever. And your end behavior, again, we're going to do our limits. So the limit of f of x as x approaches negative infinity. As I go to the left, it's approaching 0. So that's going to equal 0. And the limit of f of x as x approaches positive, that's an ugly arrow, whatever, make it work. As x approaches positive infinity, as I go to the right, you see I'm going to the right, it's going up. So that's going to be infinity. So that's going to be, again, an example where we have a growth and we have a different y-intercept. And again, those numbers can change all the time. So the last thing I want to bring up before we wrap this up is natural base. Now, if this is something maybe you remember, maybe you don't, and obviously we haven't taught it this year, but it's something you have learned before, and this is going to be an example. This helps bring up the natural base. But this is what we used to use back in the day when we would do compound interest. And when we were doing these, and this is more in Algebra 2, sometimes you even do it in middle school, depending. But in these scenarios, the part I'm going to be focusing on right now is this. And this, by the way, this is your principal, your starting amount. You'll kind of see how it matches up with that initial value, that a value. It does. This is the same thing. It's just an example of how exponential functions can get used. But what I'm going to focus on is this right here. So this would be compounding interest. So let's say we had R. R is a rate. So that would be like if you have a bank account with a 2% interest rate that gets compounded monthly. Well, when it compounds monthly, because you're going to get a new bill or a new statement each month, that N is going to be the number of times the rate is compounded. And usually when we do this, it's the number of times it's compounded per year. I mean, that can always be different, but usually it's always considered years unless we want to literally go out of our way to change it. So that's what this means. Now what I want to do is show it a quick example, and this is where you need to use your calculator and kind of follow along with what I'm doing. So what I'm going to do is I'm going to call my rate 1. And in reality, I really don't care what my rate is. It's just a number, because here's what I'm going to do. I'm going to call N as best I can. I want it to be infinity. But we can't plug infinity into our calculator. So what I'm going to do instead is I'm just, for now, going to call it 1,000. I mean, it's a big number, right? So on your calculator, what you need to do is you need to take this, and I'm just going to take, again, this part right here, and I'm going to plug in 1 plus R, which is 1, over 1,000. And I'm going to take that, and technically, again, you raise it to the n times t. So I'm just going to do this in terms of just 1 year, so I'm going to not worry about my t. And I'm just going to raise this to the 1,000th power, because n and n, these are the same numbers. So that way I don't have to worry about my t. So if you plug this into your calculator, and I actually should have that on mine, again, you can just take it into your calculator, and what you get is something about like this, 2.7169. And then what I want you to do, once you have that plugged into your calculator, there's a little button, and it depends on where your calculator is. Mine's above the division sign. If you hit second, divide, it should give you this button. It's called E. So E, if you plug that into your calculator, is approximately 2.71828, and it keeps going. But I want you to kind of see these numbers are basically the same, because I said I want to plug in infinity, which I can't do. So what I do is I plug in a big number, so it's going to give me an approximation. This approximation is approximating E. So what is E? Well, it's nature's number. I always use the example, the bank account. You're going to get a statement every month, and that's when they decide they're going to compound that interest. Well, in nature, they don't take breaks. Say, well, we'll like if we're doing radioactive decay, they're like, let's wait a month, and then we'll decay. We'll because you have a half-life of, say, a month. It's not like the radioactive matter goes from 100 grams to 50 like that. It's always decaying. And anything in nature, it's always decaying or it's always growing. It doesn't take breaks. So that if you think about it as a compounding interest, it's continuously compounding. And that's the key on anything with a natural base. Anytime you see something that says continuously, and that's what I'm going to write here, continuously, if I spell that right, sorry, compounding, what we're going to do is we're going to use this number E. Now how does it work? Well, it plugs into this equation, A equals PE to the RT. We'll use that in our applications, but for right now, this is just an introduction to it. Here's what I want you to be aware of. So this is the last little piece that I'm going to go over here. E is greater than 1. Therefore, it's an exponential growth curve. So when we're graphing it, and we're doing just the basics with it right now, it's a growth curve. So I just want you to be aware of that. It's growing. And then we have to apply it or do things with it. I want you to understand E is this number, great, but it represents something that's always growing or always decaying. In other words, if we're dealing with nature, which is why it's called a natural number, when we get into logarithms, it goes into what's called the natural log. That word nature it's not just a random word. That's where this number really comes into play. So for right now, understand the basis of where it comes from, but more importantly, know this is the number that it equals. It's an exponential growth curve. So if I'm graphing it, if I had this curve right here and I change this to an E, for all intents and purposes, we would be doing the same thing. Okay? So that's, again, a quick introduction to a natural base. We have exponential growth, exponential decay. Make sure you understand these concepts, and good luck.